Let me do this, share screen. And hopefully this will go easily. Let's do that. Let's lock this. Okay. All right. So I'm going to begin tonight with a very brief review of what we did last time. So let me pull it down here. I've kind of got it covered up here. Basically, we're in the, here, let me turn off my email. It's going to be dinging all night long. Let me get rid of that too. There we go. Come on, go away. All right, good. Yeah, so basically, we are trying to find a Hamiltonian description for classical electromagnetism. We took Maxwell's equations and we substituted for the electric and magnetic fields, we substituted their expressions in terms of the scalar and vector potentials. And then at that point, we sort of recognized that the Q's, what you might call the Q's of the electromagnetic field, are related to the vector potential because its equation of motion is second order in time, like in a mechanical system. And this more or less turns out to be correct. The Q's are tied up with the vector potential. However, the vector potential has a problem because it's got a non-physical component, the one that changes under a gauge transformation. So we fixed that by choosing a Coulomb gauge, which is one in which del dot A is equal to 0. And having done that, for various reasons, that was a good choice of gauge. And having done that, then the Maxwell's equations become equivalent to these two equations I've shown here for the scalar and vector potentials. These are completely equivalent to Maxwell's equations written in the case of Coulomb gauge. Now our goal here is to take these equations and to find a Hamiltonian for them that'll describe those equations as a consequence of the classical Hamilton's equations of motion. In order to do that, it's going to be necessary to know what the Q's and the P's are. As I just mentioned, the Q's are tied up with the vector potential. We know that, but the P's we'll need to worry about those too. And then to check to see that the equations of motion give us the right answer. Then we'll have a classical Hamiltonian description, and we'll be set up for doing quantization. So that takes us up to where we left off last time. Oh, having introduced Coulomb gauge, I then went into a fairly lengthy digression into the properties of longitudinal and transverse vector fields, which are needed in order to do manipulations in Coulomb gauge. All right, so that takes us up to the end of what we did on Tuesday. Are there any questions about that before we proceed? All right, so then the first thing I want to do is to address these equations of motion in Coulomb gauge. By the way, that dot that appears there shouldn't be there. There's no dot. It's just del squared phi. So let's look at these equations of motion which apply in Coulomb gauge. The phi equation, as you can see, is just the Poisson equation. And so we know how to solve that, the rho being the charge density. The solution is that phi of x and t is given by the integral over x prime, spatial points x prime, the charge density evaluated at x prime and t, divided by the Coulomb denominator x minus x prime, like that. That's the solution of the Poisson equation. In fact, it's a unique solution if you require that the potential phi vanish at infinity. Now, this is just like in electrostatics, but the point that I want to make is that we're not doing electrostatics, we're doing full electrodynamics. And that's manifested here by the fact that these are actually time-dependent fields. What we've got here is the scalar potential evaluated at a space and time, a field position and a field time, x and t. And you can see it's given as an integral over all of space so that it takes up all the charges in the rest of the universe, which are evaluated at their position x prime, but the time is the same as the time of the field point t. So this is a way of saying that this expression for the scalar potential has no retardation in it, that charges at an arbitrarily large distance away contribute to phi without any delay. So in electrostatics, that's okay because everything is static and the delay doesn't matter. But in electrodynamics, which we want to do, it makes a difference. So the question then is does this mean that Coulomb gauge is somehow violating relativistic causality? And the answer is no. And the reason is that you don't measure phi. What you measure is the electric field. And the electric field is given by minus gradient of phi minus 1 over c partial of a with respect to t. Now the gradient of phi is purely longitudinal. That's because if you take the gradient of any scalar, call it grad f, then it's automatically curl free. And being curl free means it's a longitudinal field. So grad phi is purely longitudinal. Moreover, in Coulomb gauge, the vector potential itself is purely transverse. That's the meaning of Coulomb gauge right here. And so what you see is that this usual formula for the decomposition of the electric field in terms of the potentials is precisely also the decomposition of the electric field into its longitudinal and transverse parts. That is, assuming we're working in Coulomb gauge. All right. Now the longitudinal electric field is minus grad phi, so it's just minus the gradient of this usual expression from electrostatics, and it would give us the usual formula for electrostatics for the electric field, except again, there would be no retardation. So phi and the longitudinal electric field are non-retarded electrostatic formulas for those quantities. And as I say, that can't be correct physically. So how then is it possible that the full electric field is properly retarded? And the answer is that the transverse electric field, each transverse here, contains both a retarded and a non-retarded component. And when you add them up, you find that the non-retarded components of the transverse and longitudinal electric fields cancel out, and what's left over is something that's properly retarded. By the way, it's easy to see why E transverse contains a non-retarded component. In the last lecture, I explained about the transverse delta function. This is a kernel of an integral transform, which is used to obtain the transverse component of a field in real space in terms of its value of the value of the total field. So E transverse can be written in terms of the full E. But E transverse is at a given point X is not determined by the full E just at that single point, but rather it depends on the values of the full electric field everywhere in space. There's an integral transform and it integrates over all of space. So once again, distant values of the full electric field contribute to the transverse component of the electric field at a given spatial point. And there's no retardation in that either. So this is how the lack of retardation occurs in the transverse electric field as well. All right. So the result of this is that Coulomb gauge kind of makes a mess of the subject of retardation. It makes it not manifest at all. And so that raises the question about why we use Coulomb gauge anyway. Why do we use it at all if it does this? This important physical effect is obscured. The reason is the following: is that a Coulomb gauge is particularly useful for systems in which the matter is essentially non-relativistic. Its velocities of the particles are small compared to the speed of light, and moreover, one of limited spatial extent. And those two conditions hold. Then what happens is that the charge density at the field time t is almost the same thing as the charge density at the retarded time. Because it isn't changing very fast or very much. And so it's a good approximation to replace the retarded time with the actual field time, and then you get a phi, which gives you a reasonable approximation for the electric field. In fact, this is precisely the electrostatic approximation that we've been using in this course since the beginning of the semester. Electrostatic approximation basically involves working only with the longitudinal electric field, ignoring the transverse field altogether. And then you've got usual formulas from electrostatics. This is what we did when we solved the hydrogen atom and a lot of other stuff that we've done in this course. But it isn't really right. And to get it right, we need to include E transverse as well, which means we need to do full electrodynamics, and that's what we're going to do. However, to go back to why Coulomb gauge sometimes has advantages, the reason it does is that the main reason it does is that in these low velocity systems that I'm talking about, the electrostatic approximation gives you the dominant part of the electric field. And so in other words, it gives you good Hamiltonians, good approximate Hamiltonians about which you can do perturbation theory to take into account the corrections coming from the transverse fields. And that in some sense is what we're going to be doing here over the next set of lectures. All right, so that's kind of the story in the longitudinal and transverse fields. Now then, go back to the original idea that I mentioned earlier is that the Q's of the electromagnetic field are connected with a vector potential A. We've decided that's probably true. The vector potential, of course, is a field, so it depends on X. And what that means is that in a sense, you've got a different degree of freedom at every X point of space. In other words, there's a continuous set of degrees of freedom of the field because of the parameter X. It gives you the location at which you evaluate the field, and it's a continuous variable. It's a continuous infinity of degrees of freedom. This is a normal situation in field theories in contrast to mechanical systems, which normally have a discrete set of degrees of freedom. Now, it's convenient by the way, when you count degrees of freedom, in a sense, the electromagnetic field has 2 degrees of freedom at each spatial point. And that's because the field the A here is transverse. And I'll explain that a little better later on. Even though it has 3 components, in a sense, one component is lost because of the transversality condition. I'll say more about that later. But in any case, at this point, I'd like to say it is convenient to study this problem using a discrete set of degrees of freedom rather than a continuous infinity of them. And in order to do that, I'm going to introduce box normalization, which is the same thing that we did back a couple of lectures ago when we were doing time-dependent perturbation theory for scattering. To make continuous variables discrete, we divide the universe up into boxes of volume V, which is L cubed, where L is the dimensions of the box, like that. And we imagine that all the physics, including the matter and the radiation, is periodic in the boxes. If we do this, then typical fields like if S, let's say we have a scalar, let's suppose we have a scalar field S of X, like this. What it means is that if S of X is periodic in the boxes, then it can be expanded in a Fourier series. It looks like this. It's a sum on wave vectors K of Fourier coefficients S sub K times e to the ik dot x. And the K values that occur here are the same K values that occur that we talked about before. The K values lie on a lattice. It's 2 pi over L times an integer vector n as integers here. And this is the same thing as what we did before when talking about boxes and scattering theory. The K here there's a lattice in K space, and the K vectors that occur in this sum lie on the lattice, like that. And if we do this, then this is the Fourier series. Fourier integrals get replaced by Fourier series when you divide the universe into boxes. Now, as a matter of convention, I'm going to split off a factor of 1 over the square root of the volume from the Fourier coefficients S sub K. And I'll sort of box that because this will be our convention for Fourier series. If we make this convention, then the inverse transform, which gives us the Fourier coefficients in terms of the field S of X looks like this. That S sub K is 1 over the square root of volume, the integral over X d cubed X. The integral is only taken over the dimensions of the box. And then we have S of X times e to the minus ik dot X. And this is the inverse transform that goes from the field of the Fourier coefficients. So using Fourier series is fairly straightforward. I just mentioned a couple of things about it. One of them is that if S of X is real, then this implies that, conversely, it implies that S sub K is equal to S sub minus K complex conjugate. These are the reality conditions as seen in K space. The Fourier coefficients are not real, but they satisfy this relation. I'll call it a reality condition. So that's one comment to make about Fourier series. Except for that, I think it's just straightforward to use Fourier series, and I won't belabor it too much more, except I will mention one thing, which is that there are certain rules for going, if you want to make the transition in which the volume goes to infinity, and you go back to Fourier integrals instead of Fourier series, then there's some rules you can write down for doing that. And I've summarized them here. And on this summary page, and I'll just draw your attention to them now. The sum on k as the volume goes to infinity turns into an integral over k multiplied by v over 2 pi cubed. That prefactor is the density of lattice points in k space, and that's why it appears there. It's just a density factor. The Fourier coefficient s sub k goes over into this quantity 2 pi 3 halves over root volume times the Fourier transform, which is s tilde of k, and using the conventions for Fourier transform that we've been using so far in this course. And finally, the Kronecker delta, which on the lattice is a Kronecker delta. It's just 0 or 1 because you have discrete points. It goes over into a factor of 2 pi cubed over volume times the Dirac delta function in the limit, because in the limit, the density of these points goes to infinity and k becomes a continuous variable. So these are easy rules to establish, and I won't use them tonight, but later on we may come back to them. We will need them later on. All right. In any case, that's kind of the setup of a box normalization. Now, to proceed, let's return to the program that we started with. Let me bring it back again. The program we started with, which is that we're interested in finding the field Hamiltonian to describe the electromagnetic field. And we're going to do this in two phases. The first phase is going to be one in which we take the free field in which the charge density rho and the current density J are equal to 0. So it's a simpler case, and it's good to do that one first, and then we'll return to including rho and J. So if rho and J are equal to 0, it means there's no matter in the universe, and all we have is field. So you can think of a universe that has light waves traveling in it, and that's about it. There isn't anything else. So that's what we're going to look at first of all. So to talk about the free field, then let's do that. Get some space here. So for the free field, in the case of the free field, that means that rho is equal to 0 and J is equal to 0. Actually, I realized there was something I meant to talk about before that I didn't mention. So let me go back to it. Let me get it on the page here. If we take, let me get another page to make it easy here. If we take these equations in Coulomb gauge, which apply in general, including the case where there's a matter rho and J around, as I mentioned earlier, you can solve for rho you can solve for phi in terms of a non-retarded potential, and I went through the discussion of that. But I want to say something about A as well. If we take the equation for the vector potential, let's take it and project it into its longitudinal and transverse components. So if I first do the longitudinal component, the left-hand side gives 0 because the vector potential itself is purely transverse. So this gives me 0 is equal to, and then on the right-hand side, I get minus 4 pi over c times the longitudinal components of the vector, of the current J. And as far as the gradient of 5, that's purely longitudinal, so that appears also. It's 1 over c ddt of grad phi. On the other hand, if I project out the transverse components of the vector potential equation, I get on the left, I get del squared A minus 1 over c squared d squared a dt squared. That's the wave operator acting on A, because A is purely transverse, is equal on the right-hand side of minus 4 pi over c times the transverse components of the current, J transverse, and the grad phi term doesn't contribute. So this is what we get in working in Coulomb gauge. Now a comment about the very first equation here. This first equation is actually of little interest to us because it turns out it's equivalent to using the Poisson equation for phi. Del squared phi is equal to minus 4 pi rho. And the continuity equation, which the current and charge density have to satisfy, or else Maxwell's equations have no solutions. And it's fairly easy to show that the combination of these two equations implies the condition on the longitudinal part of the vector potential equation. So it's in that sense is uninteresting. The real dynamical equation for the vector potential is now given here like this. And what we see is that the vector potential, which is transverse in Coulomb gauge, is actually driven by the transverse components of the current. And again, that means this is actually non-local, as an A at one point is influenced by J values at distant points because of the projector that's the transverse projector that's needed to get the transverse current. All right, anyway, that was something I meant to mention a moment ago and forgot, so I went back to it. So now to return to the question of the free field, let me set this somewhere. To return to the question of the free field, let me get it on the page here. This is where rho and j is equal to 0. So the equations of motion are now del squared phi is equal to 0, and del squared a minus 1 over c squared d squared a dt squared is also equal to 0. And a is, of course, transverse, and I won't write that explicitly, but these are the equations for the free field. Now, in the free field, of course, the Poisson equation for phi has a unique solution, which is just phi equals 0. So in Coulomb gauge in the free field, there is no scalar potential. And as far as the vector potential is concerned, you can see it's any transverse solution of the wave equation. All right, so let's talk about those solutions. Let me get some paper here. Let me get this out of the way. Put this somewhere else. All right, let's talk about the solutions of the wave equation then for vacuum light waves working in Coulomb gauge. A plane wave solution looks like this: is that a of x and t is equal to an amplitude vector I'll call C0. C just means constant amplitude vector C0 times e to the I k dot x minus omega t. There's your plane wave. And then we add the complex conjugate to this. We add the complex conjugate because the vector potential is real. We want a real answer. The k and omega that appear in the exponent here have to satisfy the dispersion relation for light waves, which is that omega is equal to ck, which is the same thing as c times the magnitude of k. And if I want to emphasize that the frequency depends on k, I can also write it as omega sub k or omega of k like this. These notations all mean the same thing. And in the context of light waves, which I'll be talking about in this lecture tonight, it'll be understood that whenever omega appears, it's related to the wave vector k by this dispersion relation, the usual dispersion relation. All right, anyway, so that's some of the structure of this formula here. Now about the amplitude vector C0, constant vector C0, this is allowed to be a complex vector. You might wonder why it should be complex when the vector potential A is real. And the reason is that the reason you need that is because you want to allow for phases of the non-trivial phases of the different components of A. So the idea is that suppose you evaluate the vector potential, or this is a light wave actually. Suppose you evaluate it at the origin where x and t are both equal to 0. Then at that point, A is just equal to C0. Well, if you want to have a non-trivial phase at that point, C0 has to be, one of the components of C0 has to be a complex number with the real and imaginary parts. And its phase in the sense of a complex number is the same as the phase of the light wave at the origin. So on the other hand, the magnitude of that complex number in the sense of complex numbers is the amplitude of the wave in the sense of the magnitude of that component of A. Anyway, this is just a way of saying that even though we're talking about real vector potentials, these amplitude vectors must be allowed to be complex in order to get the general solution. Now, on the other hand, they aren't arbitrary complex vectors because the transversality condition on the vector potential implies that k dotted into the amplitude vector C0 has to equal 0. So these amplitude vectors are actually transverse. They're orthogonal to k. In k space, they're transverse vectors. And so they have really only two independent components. They're two independent complex components. This means that altogether, the space of plane wave solutions of light waves for a given value of k constitutes a four parameter family Basically, you have the amplitudes of the two components and the phases of the two components. Those are the parameters. All right, anyway, that's just a single plane wave solution of Maxwell's equations. Now, it's not the general solution, however. We get the general solution if we form linear combinations of those solutions. So let's talk about that now. A of x and t is equal to, let's sum over all possible k values, which are allowed under the periodic boundary conditions. What we'll sum over is a vector C0k times e to the I k dot x minus omega t, like this, plus complex conjugate, where this k is now runs over all the lattice points in k space. And by the way, for convenience, I'm going to factor off a factor of 1 over root volume, because this was our conventions for Fourier series, is to do that, and it's convenient to do it. So I'll split that away from the amplitude vector C0k. Now there's a given C0, different one for each k value, each lattice point. So these lattice points in k space are now associated with these two component complex vectors, which then taken as a whole specify the entire light wave. All right, so this is the general solution then. An arbitrary light wave traveling through vacuum can be written in this form. This is in Coulomb gauge. Now then, allow me to make a definition here of a vector I'll call C sub k without the zero, which is a function of time. And it's defined as C0k times the time dependence, which is part of the light wave. So it's times e to the minus I omega t. So the CKs become functions of time. And if I do this, then the CKs satisfy an equation of evolution, which is that CK dot is equal to minus I omega CK, like that. And then the vector potential A, I can write it this way, is A of x is equal to 1 over the square root of V, volume V, times the sum over lattice points in K space, times C sub K vector times e to the I k dot x plus complex conjugate, like so. All right. In writing out this formula, I suppress the time dependence, but of course the A depends on time, and the time dependence on the right-hand side is contained in the C's. The spatial dependence is in the phase factors here of the Fourier series. All right, so this then is another way of writing the general solution. It's also of interest to write out Fourier series for the first time derivative of the vector potential. And that's obtained just by differentiating both sides with respect to time. Since ck dot is minus omega ck, this becomes 1 over root volume here. And we have the sum on k, same sum. We have minus I omega c sub k, like this, e to the I k dot x plus complex conjugate, like so. And these then give us two Fourier series for the two fields, A of x and dAdt of x. Okay, now I'm trying to keep a summary sheet here of a bunch of the formulas that we developed. And so here's the summary sheet for the next phase of the summary sheet. Let me move this, get this out of the way. Get it out of the way here. Excuse me. Yeah, here's the next phase of the summary sheet right here. Let me bring it down. This is just these. Let me bring it down. Let me try to focus it again too. It looks like it needs it. All right. These are the same two Fourier series I wrote down earlier, expressing the vector potential and its time derivative in terms of these amplitude vectors, which are now time-dependent amplitude vectors associated with the lattice points on K space, and the complex conjugate is written out explicitly. I'm focusing on A and dAdt for the following reason. Maxwell's equations expressed in terms of the vector potential involve the wave operators we saw a minute ago. That's a second order differential equation. And thus a complete set of initial conditions for that equation involves both the specification of both the vector potential A as well as its first time derivative. Now in all of this, it's understood that these vector fields are transverse because we're working in Coulomb gauge. But these initial conditions then, we need both the A and the dAdt to have a complete set of initial conditions. In classical mechanics, what you call the dynamical state of the system is a specification of a sufficient amount of information to determine the future evolution of the system. So in an ordinary mechanical system, this could be the positions and velocities of all of the particles, or it could be the positions and the momenta of all of the particles. In any case, that's the dynamical state of the classical system. Well, what we see then is that the dynamical state of the free electromagnetic field consists of these two fields, A of x and dAdt of x, taken at some time. If those are known at some time, then the evolution ever afterwards is known. Now, these formulas that I've worked out, however, show us that these amplitude coefficients, the c sub k's here, if they are known, they determine the dynamical state of the system because it gives us the left-hand side. In other words, the dynamical state is determined by the c sub k's. This is leading up to a description, which I want to describe. I want to outline it here. Is that if I form a set of objects here, let's call it A of x and partial of A with respect to t of x. As I just explained, this gives us a dynamical state of the system, and the equations of motion are the wave equation, this for the free field. However, the collection of these these collection of these amplitude vectors, c sub k, these are transverse vectors in k space. Knowledge of them implies the dynamical state of the system. And these obey their own equation of motion, which is that c sub k dot plus I omega c sub k is equal to 0. It's actually a simpler equation of motion than the wave equation here because it's an ordinary differential equation instead of a partial differential equation. Now the question then arises is since the C's determine the A's, do the A's also determine the C's? Can we go the other direction and put a question mark here? Is that possible? And the answer is yes. And here's how we know how to do that. Suppose I take A of x and I decompose it into its Fourier series using my conventions for Fourier series. It's 1 over the root volume sum on k, and then we have the Fourier coefficients a sub k times e to the I k dot x. If I do this, then the a sub k's are determined by the inverse Fourier transform or the inverse Fourier series formula. Also, if a, of course, depends on time, so the time dependence is then carried by the Fourier series coefficients. That you just do the compute the Fourier series at each different time, and then the a sub k's depend on time. So the partial of a with respect to t, then, as a field, is given by a similar expression. It's 1 over root v sum on k of the a sub k dots, like this, times the e to the I k dot x, like so. All right. Now then, so we can, given A and dAdt as fields, we can compute the Fourier series coefficients AK and AK dot. Those are computable. Now, on the other hand, we'd like to relate these to the C's. In order to do that, I want to go back to my summary sheet here, where I've written out these Fourier series in full form. And the problem is that the Fourier series here, is it's still on this page for the A, involves a sum of k with just one term, whereas when we work through the solutions, we ended up with two terms like this. One is e to the ikx and the other is e to the minus ikx. We can take this e to the minus ikx part here, and since k here is just a dummy variable of summation, I'll do it in red. We can replace k goes to minus k in that term. And if we do, then that term turns into c sub minus k complex conjugated times e to the plus ik dot x. And then that e to the plus ik dot x is the same as the factor we have here. It's another common factor of e to the plus ik dot x, which is what we have down here also in our Fourier series for A. And so then the a sub k, the Fourier coefficients of A, are actually equal to C sub k plus C sub minus k complex conjugated. And there's a similar thing you can do with the first time derivative. And so if we do that, then here's what we obtain. Here's what we obtain if we do that. We get the following equations as we get A sub k is equal to C sub k plus C sub minus k complex conjugated. And we get A sub k dot is equal to minus I omega C sub k plus I omega C sub k, C sub minus k complex conjugated like that. So we get these two equations and two unknowns like this, which allows us to solve for the C's in terms of the A's. And if you do the algebra, here's what you get. You get C sub k then is equal to 1/2 of A sub k plus I over omega A sub k dot. And you also get C sub minus k complex conjugated is 1/2 of A sub k minus I over omega times A sub k dot, like so. You get two formulas like this. Now, these formulas are not independent of one another. It turns out the second one is really the same as the first. You get it by taking the first formula, substituting k goes to minus k, and then complex conjugating both sides. And if you do and use the reality conditions on A, because A in real space is real, you obtain the equation down below. So in fact, only one of these formulas needs to be kept, and I'll just take the first one. And the point of this first formula is it shows that if you know AK and AK dot, you can calculate the C's. Well, if you know A is a field and dAdt is a field, then you can calculate their Fourier coefficients. So what that means is knowledge of the dynamical state of the system determines the C's. So to go back to what we were doing a minute ago, this does work both ways. Is that knowledge of the C's implies the dynamical state of the system, and knowledge of the dynamical state of the system implies the C's. So this can be regarded, so these series here, these Fourier series here involving this pluses complex conjugation terms, can be regarded as, in effect, as a coordinate transformation on the state space of the free electromagnetic field. That in the dynamical state of the system is specified by these amplitude coefficient vectors, just as well as it is in terms of the A's and the dAdTs. And these have simpler equations of motion, and so in some ways this is better. All right. So we're working here on convenient variables to describe the evolution of the field, and the CKs are easier than the A and the fields partial A and partial A with respect to T. All right, now the next thing that I want to say is next thing I want to talk about is polarization vectors. These vectors C sub k are transverse. I've mentioned that already. Let's do it right. K dotted into C sub k is equal to 0. They have to be transverse vectors in order to make A transverse. It's convenient to introduce now polarization vectors, and I'll tell you about them. So let me push this up. So here's the idea of polarization vectors. Let's suppose I have a K vector like this, wave vector K. This lies on the lattice now. And I'll draw in the plane which is perpendicular to K, like so. And we'll introduce two vectors, unit vectors in this plane. Let's call it epsilon hat K1 and epsilon hat K2, like this. Or collectively, there'll be epsilon hat K mu, like this, where mu equals 1, 2, describes these vectors. These are what we'll call polarization vectors. And the mu is a polarization index, which just runs from 1 to 2 to cover the two vectors. Now these polarization vectors are required to have certain properties. One of them is they're supposed to span the plane perpendicular to K. So they have to be orthogonal to K, as K dotted into epsilon hat K mu must equal to 0. And then the second thing is we require them to be orthonormal, but we do allow them, however, to be complex vectors. So they have to be orthonormal in the complex sense. So that means that epsilon k mu, complex conjugated, dotted into epsilon hat k mu prime is equal to Kronecker delta mu mu prime. That's the orthogonality condition. And with this, you can see that the two epsilon polarization vectors, along with the unit vector k hat in the direction k, form altogether a triad of vectors in three-dimensional space that you can use to resolve any vector you want. Sometimes k hat itself is called the longitudinal polarization. Just to give it a name, the light waves don't have longitudinal polarizations, but the picture suggests that you use that terminology, so sometimes it's convenient. Okay. When you study polarization of light waves in elementary courses, they're probably going to put the k vector along the z-axis like that. So let's say this is the z-axis is pointing like this, and if we have the x and the y-axis like so, you get a picture like that, and the light wave is traveling in the z direction. In that case, the polarization vectors could be taken, for example, to be x hat and y hat. These are certainly unit vectors that span the perpendicular plane. And if you use them, you have what you call linear polarization of the light wave, which means that the electric field traces out a line, just sweeps back and forth on it. On the other hand, you may also want to use complex polarization vectors such as x hat plus and minus I y hat divided by the square root of 2 to normalize them. And if you do this, these are circular polarization vectors for a light wave traveling in the z direction. One of them is right, another is left circular, right and left circularly polarized light. In this case, the electric field sweeps out a circle in the XY planes. So I assume you're more or less familiar with these features of polarizations of light waves. The only thing I'm doing differently here is that the k vector is now allowed to point in an arbitrary direction, and otherwise we're just working in the perpendicular plane in the same way. So these polarization vectors could be real, in which case you have linearly polarized light, or they could be circularly polarized, or they could be something else for elliptical polarizations. All right, so that's fairly simple construction, but it allows us to take these amplitude vectors, these c sub k's, which, as I've just explained, taken collectively, specify the dynamical state of the free electromagnetic field, and to expand them is a linear combination of polarization vectors, mu equals 1 to 2 here, of an expansion coefficient I'll call c sub k mu times epsilon hat k mu. By the way, there was one thing I forgot to say about the polarization vectors is that they form this orthonormal triad, counting k hat, they form an orthonormal triad. But that's specific to the particular value of k. A different lattice point k has a different orthogonal plane, and there's no necessary relationship between the polarization vectors in one of these planes and another one. So if you have two polarization vectors, one with a k and another one with a different k, they're not orthonormal. In fact, there's no simple relationship connecting them at all. These relations I've written down are really the only relationships that we assume about these polarization vectors. They're really the only ones we need. In any case, to go back to this decomposition here, I'm leaving an arrow off that C. I've noticed a funny thing about students nowadays is that students tend to, this means you, students tend to, I'm talking about you, students tend to leave the little arrows off of the vectors. And so you can't tell the difference between vectors and scalars. I don't know why this is. Is it because it's too much trouble? Anyway, I'm leaving the arrow off here for a good reason, which is that these are not vectors, these are scalars, which are indexed by mu. There's two of them, 1 and 2, for the two components of the C vector, which really is a vector and lies in the transverse plane. So what we now have is two complex scalars then, which take the place of the C sub k's. All right. Now then, this then leads to a representation of the vector potential, which I'll write out looks like this. A of x then is equal to 1 over root volume v. And then we have the sum on both lattice points k as well as polarization in the index mu. And then we have the c sub k mu, the complex number, times the epsilon hat k mu, times the e to the I k dot x, plus complex conjugate. And this is just a simple rewrite of the Fourier series that we've been talking about up to this time. But it leads me to a notation which is convenient, and a terminology which is convenient. Namely, we regard this series, which I've written, this Fourier series, which I've written down here, as the mode decomposition of the mode is the magic word here, as the mode decomposition of the electromagnetic field. And we say that there's one mode for each lattice point in K space as well as each polarization. In effect, each mode corresponds to a degree of freedom of the electromagnetic field, and there's 2 degrees of freedom for each lattice point in K space. And then these CK mu's here then are the quantities that really are the coordinates on the state space of the system that now take the place of the vectors CK that we were using a little while ago. Here's some convenient notation. It's convenient to have a notation for the compound index K and mu. I'm going to use the symbol lambda for this. Lambda is equal to K mu, and I'm going to call this a mode index. And if I do, then I can write this thing as just C sub lambda, and the polarization vector is epsilon hat lambda. And if we do all of that, then what we get is we get somewhere here, I thought I had it, we get a mode decomposition of the electromagnetic field in this form. Let's see, do I have it here? Yes, I do. Here's what I want. It looks like this. Here this is my summary sheet. I've summarized some things here. Here's the formula that gives the amplitude vectors in terms of the Fourier series components of A and dA dt. So this is part of the coordinate transformation. And then here is the vector potential written in this form where lambda is now this mode index equals K mu. Here it is. Here's the C lambda epsilon lambda e to the IKX and its complex conjugate. All right. Now, this can be regarded as yet another coordinate transformation where we've gone from the CK vectors to the C lambdas. It's a fairly trivial one, but it's a third coordinate transformation. In the vacuum, for vacuum light waves, there is no longitudinal field because the scalar potential is 0. So the electric field is purely transverse, and it's just given by -1 over C dA dt. And if I take the Fourier series for dA dt and write it in this mode amplitude form and divide by C, I get a Fourier series for the electric field for vacuum light waves, and that's what it is. Also, if I take the curl of A, I get a Fourier series for the magnetic field. The curl only involves the del cross just brings down IK cross from the phase factor here. The IK cross gets multiplied on the polarization vector. And so I get this Fourier series, the IC lambda and then K cross polarization vector, and then the plane wave and its complex conjugate. So we now are accumulating Fourier series here for various fields of interest, the vector potential electric field and the magnetic field for vacuum light waves, expressed now in terms of the mode amplitudes, C lambda. That's what I'm going to call these things henceforth C lambdas as mode amplitudes, because that's what they are. They're the amplitude of the wave for a given mode in this sense of the electromagnetic field. All right. Now, having done all that, let me move to another page that summarizes some of the things that we've done. If I can find it here. Yes, here it is. This is something of a summary of the dynamical state of the free field and some of the things we've done with it. We started out with A and dA dt, giving us a dynamical state in which the equations of motion is the wave equation. We then switched over to the amplitude vectors CK, and their equation of motion is a simpler equation here. And now we switched over to the C lambdas, which are just the components of the CKs along the polarization vectors, where lambda is now a mode index, lambda is K mu. And their equation of motion is really just the same as this, but the components along the polarization vectors have been projected out. So it's C lambda dot is minus I omega C lambda. And this is then giving us a sequence of, in effect, coordinate transformations. The collection of these mode amplitudes C lambda then specifies the dynamical state of the free electromagnetic field. All right. Now then, where we're ultimately going with this is we want to find the Hamiltonian, which describes the free electromagnetic field. So to do that, we're going to use some guessing. So it works like this. Let's take these mode amplitudes C lambda. C lambda dot is equal to minus I omega C lambda. That's the equations of motion. So C lambda of t is equal to C lambda initial conditions times e to the minus I omega t, like that. And let's plot the time evolution of the mode amplitude in the complex plane. They're complex numbers, so let's plot them in the complex plane. You can see the time evolution is just a motion in a circle in the complex plane. So it looks like this. If I have the initial condition here is C lambda of 0, C lambda sub 0, I mean, that's the same thing as C sub lambda of 0. And in a later time, I've got C sub lambda of t, like so. And the angle evolved in this direction, and that angle is omega t, where omega is the frequency of the mode in question. So the mode amplitude just goes around and around the circle. Now, hopefully what this will do is remind you of what we did last fall with harmonic oscillators. In case of the harmonic oscillator, we can have a Hamiltonian h, which we can write this way as omega over 2. Let's make it x squared plus p squared, like that. And we introduced a complexified classical variable, which is x plus ip divided by the square root of 2. We used units where h bar was 1, but if we restored the h bar units, you'd want to put a square root of 2 h bar in there. It makes z dimensionless if you do that. And this variable z evolved exactly like this in a circle in the complex plane under this harmonic oscillator Hamiltonian. And so this leads to a guess. If we want to find a Hamiltonian for the electromagnetic field, we need to know what the p's and the q's are. And the guess is this, is that each of these complex mode amplitudes C lambda is proportional to some constant. It's proportional to a q plus an ip, like this, that its real and imaginary parts are the q and the p of a harmonic oscillator. And if this guess is correct, then the Hamiltonian for the electromagnetic field is going to be a sum over the modes of the frequency of the harmonic oscillator, omega lambda over 2. It's the frequency of the modes, what omega lambda is, times q lambda squared plus p lambda squared. In other words, there's one harmonic oscillator for each mode, and its frequency is the same as the frequency of light waves in that mode. Now, that's what this suggests. It's a good guess. The question now is, what is this constant? Let me call the constant capital K. I'm kind of running out of the alphabet here, but I'll call it capital K. How can we determine what that constant is? Well, we can determine it by making another guess. In mechanical systems, the Hamiltonian is usually the energy of the system. So let's guess that that's true here as well. The Hamiltonian then would be the energy of the free electromagnetic field. But from electromagnetic theory, we know what that is. That's 1 over 8 pi, the integral over space d cubed x of e squared plus b squared, like so. This should be integrated over the box. Since we're using box normalization, we'll just take the energy inside one of the boxes. But anyway, this then is the guess for the Hamiltonian is the energy inside one of the boxes. So is this true? And in particular, does it give a sum of harmonic oscillators? Well, the way to find out is to take these Fourier series for E and B, which I wrote out here previously. Here they are, written out in some detail, in terms of the mode amplitude C lambdas, and to substitute in here and to do the integrals and to work this out. Let's work on this. Let's take the E squared term. That's going to be equal to 1 over 8 pi. It's going to be the integral over the box, d cubed x. And if I look at the Fourier series for the electric field, it's got 1 over root v times 1 over c, and then the lambda sum here. So that gets squared because there's 2 of them. So I get 1 over volume v times c squared. The small c is the speed of light, and the big c's are the mode amplitudes. I'm sorry about the notation, I think it's usually clear which is intended. And then what we've got is the sum. Then we got the product of two Fourier series. And let me write this out explicitly here. It's the sum on lambda and lambda prime. And the first one looks like this. It's I omega. It's I omega times C sub lambda times epsilon hat lambda times e to the I k dot x plus complex conjugated. If you don't believe me, here's the summary of it. Here you see these I omega c lambda epsilon e to the I k dot x, and there's the complex conjugate right there. And then this is then dotted into the other copy of E, which I'll write this way is I'll write it as complex conjugate minus I omega c sub lambda star epsilon sub lambda hat star e to the minus I k dot x. That's for the second copy of the electric field. Except I need to put primes on the lambda here because it's the second sum, and that means primes on the omega and on the k as well, like so. So this is the kind of integral you need to do to get the e squared contribution to this expression for the Hamiltonian. Now, I'm going to outline this calculation. There's obviously four terms in multiplying these two Fourier series together. Let me take the term that involves the cross term for the first term of the first electric field series and the second term of the second series. Let's do the algebra, some of the algebra on that. Let's look at the c lambda prime star term of this. That's the one indicated by the arrow up here. And that's equal to, as you can see, 1 over 8 pi, copying from up above, volume v c squared in the denominator, integral d cubed x, which is taken over the box. And then we've got a double sum here. And instead of lambda, I'm going to break the lambdas into k's and mu's, k mu and k prime mu prime, like that. And then multiply these two together. The I times minus I is 1. Omega times omega prime, I'll copy that. The polarization, or the C's come next. I have a C sub lambda, which is the same as CK mu. That's multiplied by C star lambda prime, so that's C star K prime mu prime. Then we have the polarization vectors, which are dotted into each other. That's epsilon hat K mu, dotted into epsilon hat K prime mu prime complex conjugated. There's a dot product. And then the phase factors are e to the I k dotted into x minus, no, sorry, let me do it right. The phase factor that goes in here is e to the I k minus k prime dotted into x. Okay, I hope that's clear. All right, now, this integral is all doable. If we integrate over the volume of the box, which is what this integral is taken over, divided by the volume of the box, and we integrate the spatial, the only thing that depends on the spatial variable x is that phase factor there. Then by the orthonormality of essentially these plane waves, we just get a Kronecker delta and kk prime for the wave vectors of the two modes. That then allows us to do the k prime sum on replacing k prime gets replaced by k. That will also cause omega prime to get replaced by omega. If we do this, then in the algebra then turns into 1 over 8 pi c squared. We have a sum now simply over k mu and mu prime. The omega prime turns into omega squared because the two omegas are equal. We then have a ck mu for the first factor here, and the second factor becomes c star k mu prime. The two k values are now equal. We have the dot product of polarization vectors epsilon k mu dotted into epsilon hat k mu prime complex conjugated. Now you see the two k vectors are identical. And that's it. All right. Now, this dot product, because the polarization vectors are orthonormal, is a Kronecker delta mu mu prime. And so that allows us to get rid of the mu prime sum. And if we do that mu prime here, it turns into a mu, and so the two C indices are the same. So this becomes then equal to 1 over 8 pi c squared times the sum on just a single k mu sum. We have omega squared like this, and then we got the absolute value of ck mu squared like that. And if I change notation slightly, it becomes 1 over 8 pi c squared sum over mode indices lambda omega squared times c absolute value of lambda squared, like so. All right. So this is just one of four. So this is how you do the calculations. So this is just one of four terms in the calculation of the electric field contribution to the total energy of the system. It's just this one cross term. If you work out the other cross term, you find that it's identical with it, and it doubles the answer. If you then take the b squared term with the magnetic series and multiply the magnetic Fourier series together, you find their two cross terms are also equal, and in fact are equal to the electric terms that we just did. So altogether, that one calculation I just did gets multiplied by a factor of 4 to take care of all of those terms. As far as these direct terms that go like this, both in the electric field and in the magnetic field, if you compute all 4 of them and add them up, the electric and magnetic contributions both, you find they cancel and give you 0. And the result then is that the energy in the electromagnetic field, calculated from standard electromagnetic theory, is this answer we just got a minute ago multiplied times 4. So I'll write h here and put a 4 there like this. This, of course, turns into 1 over 2 pi c squared, like so. On the other hand, the c sub k's here, c sub lambdas here, are supposed to be equal to our constant k squared times q lambda squared plus p lambda squared. That's because we were guessing a minute ago, remember, that we guessed that the c lambdas were given by a constant times a, with real and imaginary parts being the q's and the p's, just like for harmonic oscillators. And so what this shows is that our guess that the Hamiltonian was a sum of harmonic oscillators is correct. And in order to make it come out to be the answer we expect with harmonic oscillators with the right frequency, which is a sum on lambda omega lambda over 2 q lambda squared plus p lambda squared, we have to get this k right. Getting the k right is just a matter of just following through it and getting these coefficients correct. And if you do, you'll find that k is equal to the square root of it's equal to the square root of let's see, what am I missing here? I'm what is k equal to? I've lost track of it. K is equal to, oh yeah, it's equal to pi c square root of pi c squared divided by the frequency omega lambda, like so. And so this ends up telling us then that the c lambda then is equal to the square root of pi c squared divided by omega sub lambda multiplied times q lambda plus ip lambda. And that gives us you see, the canonical coordinates, the q's and the p's for the electromagnetic field. Now, if I can go back to my summary sheet then here, one of them here, the one I'm looking for. Here it is. This traces what we've done in transforming the dynamical state, starting with the fields A and dAdt, going to the vector amplitudes of the modes, going to the scalar amplitudes of the modes after introducing polarization vectors. And now there's another step as well, which is that there's another coordinate transformation, and this takes us to the collections of the q lambdas and the p lambdas, like so. And we also now know what the Hamiltonian is. So what this does then is this completes the program that we were trying to carry out for the free electromagnetic field. And we find that there's a sequence of well-defined coordinate transformations, so that ultimately you see the q lambda and p lambdas are functions of the a's and a dots up here, the a's and dAdts. Given those, you can find the q's and the p's, and all the other variables in between. And moreover, we now have the Hamiltonian, which is in fact equal to the energy in the field, and it is a sum of harmonic oscillators, one for each mode. All right. These modes, of course, are I mean, there's one harmonic oscillator for each mode of the field, meaning a K vector and a polarization. This is really not surprising because light waves are kind of oscillatory phenomenon, and you'd expect them to be described by some kind of a harmonic oscillator, but we've got the details of it all worked out here. You can also see where this is going to go in quantization. It is that each mode of the electromagnetic field will turn into a quantum oscillator, and it'll have energy levels that go like, multiples of h bar omega. Well, those energy levels being multiples of h bar omega represent photons in that given mode. The number of photons is the number of excitations of the oscillator. This is getting ahead a little bit by about a lecture and a half or something, but that's where we're going with this. But in any case, for now, we're still at the classical level, and we've achieved our goal, which was to get the classical Hamiltonian description so far just of the free field. Now, before I go on, let me pause and ask if there's any questions what we've done so far.
So I thought when we were writing down the C's, isn't Q basically just A and P basically just A dot, or did I make a typo in my notes? Up to normalization?
Isn't what just A dot?
Sorry, these Q's and P's we just found.
Yes.
After you break A into all the modes and stuff, isn't Q basically just A and P basically just dA dt, or up to like some constant factors?
No, the Q's and the P's are the real and imaginary parts of the mode amplitude, the complex mode amplitude C, times a multiplicative factor. It's actually given right down here.
Right, but isn't the inverse transformation of the CKs at least basically just
at the bottom
we know the AKs are real?
So at the bottom of the page
Right.
shows the Fourier series. So this is A of X, and here's the Fourier series for A. Each term is it's a sum over modes, and each term is a sum of complex conjugate terms. But each of these two terms is complex. The C's are complex. The Q plus IP lies inside the C. But the polarization vector is here too, and it may be complex, and certainly the phase factor is complex. So
maybe the right thing. Oh, go ahead.
Yes, so the A is being written in terms of, if I substitute in for the C's, I get A's explicitly in terms of the Q's and the P's. But it's not just the real and imaginary parts of A, no, because there's polarization vectors and the spatial dependence as well.
So maybe what I should have said is if we have linearly polarized light, then because of the inverse transformation written right there, though, that should be roughly the idea.
Well, even there, you got the e to the ikx, which is complex.
Right. Okay. Yeah.
We are trying to say that the CK, the expression CK equals 1/2 of AK plus I omega AK dot means that the AK is sort of like the QK and the AK dot is sort of like the PK.
No, it isn't as simple as that. It's the QK and PK are the real and imaginary parts of the CK. The AK and AK dots are not real. They're complex because they're Fourier coefficients. Even of a real field, the Fourier coefficients are complex. If a field is real, there's a constraint on the Fourier coefficients. In the case of A, for example, it says that A sub k is equal to A of minus k complex conjugate. Nevertheless, the AKs themselves are complex numbers.
I see now. I think I was just confusing myself from reading off the inverse transformation wrong. Thank you.
Yeah. There's a lot of details floating around here, and you kind of need a chart, a flow chart here like this to keep track of it all. But if you get that, you'll see that it's not as simple as that. All right, now, so that takes us up then to what I want to do with the free field. And now the problem in the remaining 10 minutes is to work on the interacting field. So let me do that. So get a new piece of paper for the interacting field. So for the interacting field, in first place, the equations of motion are now different. We've got del squared phi is equal to minus 4 pi rho. There's a rho around. we have del squared A minus 1 over c squared d squared a dt squared is equal to minus 4 pi over c times the transverse components of the current. All right, so this is now in the presence of matter. If we're going to include matter in the dynamical system, we need to have some model for the matter. I'm going to choose a model which is non-relativistic, a collection of non-relativistic point particles. So let's talk about particles here. Let's talk about the positions of the particles. I'll denote this as r sub alpha, where alpha goes from 1 up to n, so the alpha indexes the particles. If we talk about the velocities, let's call that v sub alpha in the same range. If we talk about the charge of the particles, let's call that q alpha. The mass of the particles, let's call that m alpha, and I think that's enough for describing the particles. If we do this, then the charge density rho of x and t is given by the sum over the particles alpha of the charge q alpha times the Dirac delta function of x minus r alpha, the particle position, which is a function of time. Particle position is a function of time because the particles move around. In this notation here, the x stands for a field point, and the r alpha stand for the particle positions, as I just indicated up above. And as you see here, so this is the charge density. It's zero everywhere except right on top of the particle, and there it's a delta function singularity. But the x dependence comes from inside the delta function. Notice also that the time dependence of the charge density comes about because the particles are moving around. R alpha is a function of time. The x here is a field point, and it's not a function of time. Likewise, the current J of x and t is the sum over the particles alpha of the charge q alpha times the velocity v alpha times the same Dirac delta function x minus r alpha of t. I don't know if you did this kind of stuff back in Physics 209, but you might have. It's the kind of thing you could cover in a course like that. In any case, these expressions for the charge density and current satisfy the continuity equation, d rho dt plus del dot j is equal to 0, as you can easily check. That's good because if they didn't, then there's no solution to Maxwell's equations. All right. Now then, with this charge density, then we can now talk about the solution to the Poisson equation for phi, and that is that phi of x and t. Well, I gave a formula earlier in terms of an integral over the charge density, but if the charge density consists of delta functions, you can do the integral. And so what you get is that phi of x and t is the sum on alpha of q alpha divided by the Coulomb denominator, which is x minus r alpha of t. This is an obvious formula from electrostatics. It just gives us the potential as produced by particle of charge q alpha at position r alpha, and it's non-retarded. You see the scalar potential depends on the instantaneous position of the particle. That's because of the use of Coulomb gauge here. In any case, that's what phi is. All right. Now then, likewise, I could take the gradient of this, get the electric field, and it would also be a non-retarded expression. Notice that the scalar potential phi is actually a function of the particle positions r alpha. The x here is not a dynamical variable at all, but it's merely the point at which we measure the field. But the phi is a function of the particle positions, and that means that in Coulomb gauge, the scalar potential is not a dynamical variable which is independent of the matter degrees of freedom. It's a function of the matter degrees of freedom. We discussed that earlier in connection with quantum mechanics. The same thing is true, by the way, for the longitudinal electric field, which is just minus the gradient of phi. It's also a function purely of the matter degrees of freedom, that's to say the positions of the particles. On the other hand, the transverse fields are real dynamical fields, real dynamical variables with their own equations of motion and so on. Okay, so this is some of what comes out of the in the case of solving you can partially solve the equations of motion in the interacting field. At least the longitudinal fields, you can do that. Now, let me outline the strategy of where we're going to go with the interacting field. The strategy is to take the sequence of coordinate transformations, which we carried out for the free field. Let me bring them back. Take this sequence of coordinate transformations and to carry out exactly the same coordinate transformations now also for the interacting field. So the definition, for example, of the CKs or C lambdas or the Qs and the Ps ultimately back in terms of the As and dAdTs will not change when we go to the interacting field. What will change are the equations of motion. In fact, what happens in the interacting field, it's already obvious from looking at the equation of motion up here, is that what used to be harmonic oscillators in the free field are going to turn into driven harmonic oscillators because there's a right-hand side here involving the current, which is the matter. So the matter is the matter degrees of freedom are going to drive the harmonic oscillators for the field. That's going to be the general nature of it. When we drive a harmonic oscillator, we normally don't change the definition of the Qs and the Ps, we just change the equation of motion. And that's what we're going to do here too, is to keep these coordinate transformations all the same, but change the equations of motion. Actually, as far as the first one, this dAdt, the wave equation, we know what that one is already. Instead of a 0 here, we get minus 4 pi over c times j transverse. That's what came out of doing the actual equations of motion in the presence of matter. Let's work on what how the equations of motion change for these other subsequent variables as well. Let's do the C variables next. Let's work out what their equations are. Maybe I have time to do that before we run out of time tonight. So the problem then is to compute. So here's the deal. We'll do it like this: is that the C sub k dot plus I omega C sub k. This is equal to 0 for the free field. Let's work out what it is for the interacting field. Let's work out the right-hand side here. The way to do this is to take the coordinate transformation, which is on my summary sheet here. The summary sheet is very convenient, except I have so many of them floating around, I can't find it when I need it. Here it is. The CK is given by 1/2 the AK and I over I omega AK dot. It looks like that. So let's do this here. So this is equal to, let me try to put it up here so you can see it all in one page. I want to compute this quantity using the CK defined in terms of that. So there's a first term here. This is equal to a 1/2. The first term, I take the time derivative of the AK. So I get AK dot. And the second term is plus I over omega, and then I get an AK double dot. That takes care of this part. And then we get plus I omega over 2 for the CK itself. That's the AK plus I over omega AK dot. And if you look at this formula for a little bit, you'll find that the terms involving AK dots cancel. There's a 1/2 I omega over 2 times I over omega gives me a minus 1/2, and that cancels. So the AK dots go away. And then if I take the, let me factor out the 1/2 and the I over omega, so I get I over 2 omega like this. And then I get an AK double dot from this term. And then taking into what's left over there, it turns out that's plus omega squared times AK like so, like this. So this then is equal to, down here is equal to that. And we get a non-zero result. Now then, this, however, as it turns out, is equal to I over 2 omega times, here, I better not do it. But let me leave this calculation as it is for the moment, and let's work out what this quantity in the parentheses are here: AK double dot plus omega squared A sub k. The way to do that is to go back to our equation of motion. For the, yes, it's right up here at the top of this page. Can we see it right here? If I take the A equation of motion and subject it to a Fourier series, the del squared operator goes into minus k squared. So this turns into minus k squared times A sub k. The second term gives me minus 1 over c squared times A sub k double dot. And the right-hand side gives me minus 4 pi over c times j transverse sub k. Or that's just the Fourier coefficient. Let me get back on the page here. This is just the Fourier coefficient in the Fourier series for j transverse. If I change signs on this and multiply through by c squared, what I get is A sub k double dot plus omega squared times A sub k is equal to 4 pi c times j perp sub k. In other words, we get a driven harmonic oscillator for the Fourier coefficients of A. However, on the left-hand side is exactly what we got down at the bottom of the page here in calculating this quantity for the time derivatives of the C's. And if I plug that in up here, 4 pi c over j perp k, what I get is this becomes equal to 2 pi I c divided by omega times j perp sub k. And so if I may go back to our summary sheet here, the equations of motion of the C sub k's in the interacting field is going to be this, is C sub k dot plus I omega C sub k is equal to the right-hand side, which is 2 pi IC divided by omega times j perp sub k. And this then is the equations of motion of the mode amplitudes in the interacting field. As you see, there's a driving term on the right-hand side, which drives, in effect, drives the harmonic oscillators. Okay, so I better stop there. I'm most of the way through the second phase of this, which is to complete the determination of not only the equations of motion. The Q's and the P's aren't going to change, but the equations of motion will. We'll determine the equations of motion of these various variables as we move down the line. And then the determination of the Hamiltonian, which by means of Hamilton's classical equations reproduces these equations of motion. And therefore, ultimately, the equations of motion of the interaction between the electromagnetic field and the matter. Okay, so let me stop there and ask if there's any questions. Anybody got a question? All right, if there's no question, we can call it a day or call it an evening. I will stop sharing. Last call for
questions. I do have one quick question.
All right, sure.
So what is J parallel sort of doing just in general, if it's not affecting the physical part of the vector potential?
Yeah, so the J longitudinal appears in
it
appears in the continuity equation. So the
Right.
you see the continuity equation's got del dot J, right? It's d rho dt plus del
Right.
dot j equals 0. So del dot j is the same thing as del dot j longitudinal. The transverse part doesn't contribute to that.
I
So
see.
the transverse part of the current doesn't contribute to the time derivative of the charge density.
I see. Okay.
So the
So
transverse components of the field are driven by the part of the J that's disconnected from the charge density. It's a good question.
interesting.
But
Yeah.
it is. There's a lot of interesting stuff in this if you look at it. Yeah. So are there any other questions?
Sorry, I guess I just have one more follow-up. Like if I'm just thinking about rho and J in terms of like a single particle's world line or something, like
Yeah.
is there an easy way to see? Because I guess I would imagine like, yeah, I guess I don't know how to picture exactly where. Is there an easy way to picture which projections or what if I'm just thinking about a single particle?
What kind of projections are you thinking about?
I guess I'm just thinking like, if I just have some, like just a single particle, and I think about its world line with charge Q, let's say, like,
Yeah. So
what does the each piece look like?
Yeah, so that's a space-time description of the classical motion of the particle, right?
Right.
Okay, so now you're wondering about the rho and the j for that.
Yeah.
Yeah,
And I'm
so
wondering what the longitudinal and transverse pieces look like for that.
well, you might wonder first of all, what does the rho and the j look like? I mean, I've got formulas here, but they aren't covariant. So
Yeah, I guess that's fair.
there's a covariant way of writing them. You need to integrate along the world line. Actually, you have a delta function in there that'll give it to you. So we'll probably see that later in the course.
Okay. Yeah.
Now, the decomposition into transverse and longitudinal fields is not Lorentz covariant. If you do it in one Lorentz frame, it's a different result than if you do it in a different frame. That's another issue about Coulomb gauge, is it's specific to a given Lorentz frame.
Right. Yeah. Well, I guess I was imagining like there's like an analogous, maybe not the same concept, but like an analogous concept that would be Lorentz invariant. But
Yeah.
maybe not though.
Yeah.
Like sort of like a longitudinal piece of the total for current that is the continuity equation in a sense, and the transverse piece that in total would be the, maybe that's not right, but that's something I was thinking.
Yeah. Okay, any other questions? If not, then thank you for your attention, and hope to see you soon. By the way, more people should come to office hours. I think they're always fun. So I just usually get 2 or 3 people. So I'd be glad to see you if you want to come. All right, then good night, and I'll see you soon.